This lecture is about recursive types. So the problem that we'd like to address is that the type system that we have developed so far does not account for recursive data structures or inductive data structures, such as list or binary trees, and so on. We can even think of natural number as recursive data structures because you can define this natural number inductively as either 0 or successor of natural number. So in any case, the type system that we developed so far does not have any type construct for expressing recursive data structures. So in this lecture, we'd like to extend the language for type system so that we can express directly recursive types. So here is an example. We'd like to create binary trees of natural numbers. Let's use this net tree to mean binary tree of natural numbers. So it is a binary tree, so it is either a singleton leaf node or it could have two smaller child subtrees. So in the first case, in this case, this natural number tree is composed of a singleton leaf node with a natural number, for example, 3. In this case, this binary tree has two subtrees, so we have the first subtree of type net3 and the second subtree of type net3. So our goal is to introduce some new type construct so that we can express types for binary trees of natural numbers defined in this way. So let's start with some informal way of defining this recursive type. So let's consider this equation. Natural number 3 is equal to natural number or pair of natural number 3. So you may read this symbol as equality or congruence. Both options are fine because we are going to give how to interpret this equality or congruence later. So we can think of this recursive type net3 as a solution to this equation. Or we may assume that this recursive type net3 satisfies this equation. Because intuitively, in order to create natural number 3, you have to take one of two choices, this one or this one. If you take the left choice, then you are going to create a singleton leaf node consisting of natural number. And if you take this right choice, you are going to provide two subtrees, child trees of type, the same type, natural number 3. So informally, we may assume that the recursive type net3 satisfies this equation. Now, the question is, how do we interpret this symbol, equality or congruence? So in the programming language theory, there are two approaches to interpreting this equation. The first is equi-recursive approach, and the other is iso-recursive approach. So it turns out that we are going to take this iso-recursive approach, which will be useful for implementing recursive types in your programming assignment. But let's briefly talk about this equirecursive approach, which stands in contrast to this iso-recursive approach in interpreting this equation. In equirecursive approach, this symbol is literally equality. This symbol literally means equality. So what that means is that suppose that you have an expression of a type net plus natural number 3 times natural number 3. So it's a sum type. It's an example of a sum type. But because we assume equirecursive approach, this symbol is interpreted as equality. So therefore, we have this equation. And under this equation, this is equal to natural number 3. So you started with an expression of this sum type, but you in fact created an expression of type natural number 3. So the conversion is implicit, it's automatic, because these two type expressions are equal. Conversely, suppose that you have an expression of a type natural number 3. Then you may interpret it as this sum type because we have this equation. It's literally equation, equality. This type net3 is equated to this type. So they are indistinguishable. The conversion is automatic. So in order to see how we actually created this natural number 3, for example, with a singleton leaf node or from a pair of child subtrees, you can directly perform case analysis because this natural number 3 is equal to this sum type. So that's the idea behind this equirecursive approach, where we read this symbol as literally equality. And now let's talk about this iso-recursive approach. In the case of iso-recursive approach, this symbol is not equality, but this recursive type allowed us to almost equate, not completely, almost equate this type and this type because the type system provides these conversion functions. So in the case of iso-recursive approach, this type, natural number 3, and this sum type are not equal, but they are isomorphic in some sense. Isomorphic. Or there is some isomorphic relation between this recursive type and this sum type. So what that means is that although these two type expressions are different, they are not equal, they are not the same, but they have the same structure essentially. So therefore, you can convert one to the other. If you want, you can convert this natural number 3 to this sum type. You can expand it. Or you can compact this sum type back to this natural number 3, this recursive type. So that's the iso-recursive approach, where the key idea is we do not equate these two types. They are not equal, but they are almost equal in the sense that there is an isomorphic relation between these two types. And what that means is that you can always convert one to the other. You can expand this recursive type net3 to this sum type, and also you can compress this sum type back to this natural number 3. So that's the idea behind iso-recursive approach. Then how do we convert between these two types. When you declare or when you introduce a recursive type, natural number 3, then what happens is the type system creates these conversion functions for you. So in other words, when you create this recursive type, the type system creates a conversion of two conversion functions. The first is, it's called unfold. Let's say unfold special. Sorry about this. So when you create a recursive type N3, the type system creates two functions for you. The first is unfold, specialized for this net3, and what it does is it unfolds. It takes a natural number 3 and unfolds it to create this sum type 3 times N3. And the other function performs the opposite. It folds. So what that means is that it takes this sum type and folds it. So again, to summarize, when you introduce your own recursive type, natural number 3, according to this isomorphism, then the type system creates two functions for you. The first, unfold, and the other, fold. And let's see how we can put these two functions to use in practical programming. First, how to create. How do we create natural number 3? If you read the specification of these two functions, you can create this natural number 3 by creating a value of this type and then applying this fold function. And that complies with our intuition about how to create this natural number 3. In order to create natural number 3, you take either the left branch, that is, you create a singleton leaf node with a natural number, for example 3. That's the first way of creating natural number 3. Or the other way is you provide somehow smaller subtrees and then create a larger one. So that's so there are two ways to create natural number 3, this one and this one. So in this case, what you do is, first, you have this natural number, and from this natural number, you create this sum type. So for instance, let's say you have natural number 3. Then you apply injection left with annotated type natural number 3 times natural number 3. Then this guy has a type net. The whole injection term has a type net plus net3 times net3. Now you have created an expression of this sum type. And then you apply this fold function. So you apply fold here. Fold specialized for this recursive type, net3. Then this is going to have a type net3, which is precisely the way that you create a natural number 3 from a single natural number. So this corresponds to the first way here. And what about this one? Suppose that you have a pair of natural number 3s. So let's just say you have an expression E of type natural number 3 times natural number 3. This is the product type. So what that means is that you have two smaller natural number trees as indicated by this product type. Then you are ready to create a larger natural number tree. So you have this one and this one. Now you are going to create this larger natural number tree. But in order to create a natural number tree, this net tree, you have to eventually go through this function invocation. You have to invoke this function at some point. So in order to do that, you have to create an expression of this type. Now, instead of injection left, now you are going to take injection right with the annotated type net. Then this one has type, this product type. So this injection right expression E is going to have type net some type natural number 3 times natural number 3. So remember that this expression E has a type natural number 3 times natural number 3. Now we are ready to apply the fold function for natural number 3. You have created an expression of this sum type. Now it's just a matter of applying this fold function. So you apply fold natural number 3, then the whole expression becomes of type natural number 3. So that's precisely the second way of creating natural number 3. You somehow prefer to smaller natural number trees. So you have this expression E of this product type, and then you create this sum type, and then you apply this fold. Then you create this natural number 3. So that's in fact how you create natural number trees in functional programming. So we have seen how to exploit this fold function in order to create values of this recursive type. So remember that when you declare this recursive type in your source code, the type system automatically creates these two functions for you. And we have just seen how to use this fold function. Now, let's see how we can use this unfold function. Unfold function is basically it allows us to inspect the contents of natural number 3. It literally unfolds this natural number 3 and exposes what is stored inside. So what that means is that we can use this unfold function to see how this natural number 3 was actually constructed. Was this natural number 3 was constructed through the first way or according to the second way here? So we don't know yet. So you have to first unfold it to see which is the case. So this reminds us of the pattern matching in functional programming, and it turns out that that's precisely what happens when you perform pattern matching on recursive types. So let's see how this thing works. So remember that unfold net has a type given me net3 not net3 given me a natural number 3, then I'm going to unfold it, literally unfold it, expand it into this sum type, net sum type net3 times net3. So now suppose that you have an expression of type natural number 3, and we don't know if this natural number 3 is a singleton leaf node or contains two child subtrees. We don't know yet. So what we do is we just unfold it. So this is not net. Sorry, this is natural number 3, and then you unfold it, and then it gives us back this type net, sum type, net3, net3. Now the problem is much easier because now we have this sum type. So we can, for instance, perform case analysis on this unfold natural number 3 expression E of injection left x blah 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 or injection right blah blah blah. So if this natural number 3 was indeed created with a singleton natural number, then at runtime we will take this left branch, and this variable x is going to be bounded to the actual natural number. Or if the natural number 3 was indeed constructed with two smaller child subtrees, then we are going to take this right branch, and this variable y is going to be bounded to this pair of natural number trees. So that's how we use this unfold. So let's summarize and further formalize the development. So remember that we can think about an equation of this form. Natural number 3 is net sum type natural number 3 times natural number 3. Now let's formally extend the syntax for types. And the idea here is we can think of N3 as solution to this equation, solution to whatever equation we are going to write here. And the equation is alpha equals net plus alpha times alpha. And this makes sense because in this equation, if you substitute net 3 for alpha, then we go back to the original equation. So therefore, literally, net 3 is a solution to this equation. Now, let's introduce new syntax to denote this one, solution to this equation. And the syntax is mu alpha dot net plus alpha times alpha. So this new syntax looks a bit complicated, and it actually looks scary, but it's nothing but solution to this equation. Alpha is equal to net plus alpha times alpha. So instead of saying solution to this equation, we'd like to take a shorthand just for brevity. So this one can be always this syntax can be expanded to solution to this equation. Now we have to extend the syntax for types. So it includes all the types that we have developed so far. And first, we introduce a new notion called type variable. So remember that this one stands for solution to this equation. So this is equation. And in every equation, you have at least one variable. So for instance, this is an equation, and you have a variable x here. Likewise, in this equation, it's actually a type equation. You have to have a variable, and the variable is this alpha. So for historical reason, we call these type variables using Greek letters. So this is called a type variable. It's a variable because it governs the equation. its type equation, and its type variable because the solution is a type, not a natural number or integer. The solution is going to be a type, something like a natural number 3. So it's called a type variable. So first we have the first component that comes to this new definition of types is type variable. And we use these Greek letters alpha, beta, gamma, etc. And then we have the syntax for recursive type, which is new alpha dot a. So this is the new definition of types. Now, what happens when you declare recursive type? Now, what happens when you declare a recursive type C defined as mu alpha dot a? So at first, this notation looks quite confusing, and but we have seen a perfect example already. So for example, we have natural number 3 is mu alpha dot net plus alpha times alpha. So this is the new syntax for types. Now suppose that you introduce new recursive type. For example, this one. Then what happens is the type system creates two functions for you. The first is fold C, and the second is unfold C. And this fold C has type C for alpha A arrow C. So this looks quite confusing, but it's actually quite simple. So let's see the example here on the right side. Fold net3 is going to take net plus net3 times net3 and returns net3. And this C for alpha A is basically this corresponds to this type expression. You take this one and substitute the solution C for alpha. So if you substitute net3 for alpha here, you get back this one. So this is the type for this fold C. And unfold is the opposite. It takes C and returns C for alpha in A. So for instance, unfold net3 is going to have type, give me natural number 3. Then I'm going to unfold it or expand it. So it returns net plus net3 times net3. So that's pretty much the key idea in this ISO recursive approach to interpreting recursive types. And we can formalize further because this fold C is the language construct that are provided by the type system. So in other words, when you declare this recursive type C with this recursive type expression, then the type system creates these two functions for you. But these are not actually lambda abstractions. They are provided by the type system, so they cannot be rewritten as existing lambda abstractions. They are not functions. So you have to provide the type system and reduction rules. Then what are the typing rules? The typing rules are easy. You just transcribe this specification into a corresponding typing rule. So for instance, what is the typing rule for fold C expression E? Well, expression E must have C for alpha A, then for the C, E is going to have a type C. We just rewrite this specification into this typing rule, where C is this recursive type. So this one gives us this typing rule. And what about this one? So it's also similar. Unfold C expression E is going to have a type this time C for alpha A. This one, provided that expression E has a type C, where C must be a recursive type defined this way. So because this fold and this unfold construct are not lambda abstractions, they are not functions, so we have to provide these typing rules, this one and this one. And what are the reduction rules? Let's assume call by value. Suppose that you have a fold C expression E. So in general, this expression E is not a value, so you keep reducing it. So if expression E reduces to expression E prime, then fold expression E reduces to expression E prime. So eventually this one will turn itself into a value. And what about unfold? Unfold is similar, but with a key difference actually. First, this case is easy. Let's say expression E reduces to expression E prime, then unfold E reduces to unfold E prime. So that's easy. But what happens eventually? So unfold expects, if you go back to this type specification or this typing rule, unfold actually expects an expression of type C with a recursive type, something like a new alpha.a, or expression E is going to be of a type natural number 3. Then what happens if the whole expression is well typed? What kind of expression do we expect by evaluating this expression E? If you look at these two type specifications, we realize that the only way to create a value of a type C, this recursive type, is by applying fold. That's the only way. Now, this unfold is expecting an expression of type C. So unfold is expecting an expression of type C. So it must have a type C, and the only way to create the value of a type C is by applying this fold C. So if everything goes all right, then you should have unfold C. The argument should reduce to actually fold C V, because this unfold is expecting an expression or a value of a type C, and the only way to create a value of a type C is by applying this fold. If we look at the example of natural number 3, in order to create a natural number 3, you have to eventually apply this fold function after creating a value of this sum type, either from this singleton natural number or from this pair of natural number 3s. Eventually, you will have to apply this fold function. So if everything goes okay, if this expression is well typed, then thanks to the type safety, this expression E will eventually produce this fold expression. In that case, we fold this value and then unfold. So these two functions cancel each other in some sense. So you will produce value v. So that's the reduction rule. I will leave it as an exercise to figure out why we don't have something like this one. Fold C, unfold C. So that concludes the development of iso-recursive approach. Iso-recursive approach to interpreting recursive types.